Unit 3, Introduction, Newton's Laws of Motion. In the first two units we were looking at kinematics, which is the study of the way in which motion can be described. How fast am I traveling? How far have I gone? Where have I gone? For the next three units we're going to look at dynamics, which is the way in which motion can be explained. What caused me to move in a certain direction? What caused me to accelerate? What were the causes of my motion? The basis for the dynamics unit is Newton's three laws of motion. Newton's first law of motion states that an object at rest will remain at rest, and an object in motion at constant velocity will remain in motion unless acted upon by an outside force. So what this basically means is if a rock is sitting still on the ground, it's going to stay that way unless something pushes it or pulls it. And if a ball is rolling down the hallway, it's going to keep rolling in a straight line. That's what constant velocity means. Straight line, same speed. Because remember, velocity is speed with direction. So it's going to keep doing that until something acts upon it. A force pushes or pulls it, causing it to change its motion. So objects at rest and objects in motion at constant velocity are the same thing. They all have zero accelerations. So to put it in a visual way, if all forces are balanced, meaning nothing is overcoming something else, there's no extra pushing or pulling, everything balances itself out, then you have either two things and they're both identical. You have an object at rest with zero velocity, an object in motion with a constant velocity. Neither are accelerating, which means they have the same motion, and the object at rest will stay at rest, and the object in motion at constant velocity will stay in motion at the same speed and the same direction. So if we're talking about balanced forces and forces pushing or pulling, we have to identify what a force is. A force is a push or a pull exerted from one object onto another, resulting in a change of motion for the second object. So that's the big thing right there, is a change in motion. Now, forces, you encounter them all the time. Pushes and pulls on certain things. It's got to be from one object onto another in order for this motion change to work. There are two types of forces. There are contact forces, where the force is between two objects that are physically in contact with each other, like pushing a door open or pulling on your door handle for your car or kicking a ball, stomping your foot on the ground. These are contact forces. Other forces are long-range forces. These are forces that have no physical contact between the two objects. They happen over a long distance. And I'm sure you can think of one, for example, it's holding you in your seat. So here are some examples of contact forces. Friction is one. If you rub your hand along a table, you can feel friction. Tension inside of a rope, what we're going to call a normal force, which is a mathematical expression. We'll get to that later. An applied force, if I'm pushing something. Spring force we don't really talk about, but that's the tension inside of a spring. And air resistance is the force of air as something is in free fall, acting upon you. Air resistance is pretty much the same thing as friction, but it's the friction of air acting on an object that's falling. Some long-range forces, for example, are gravity, which attracts one piece of matter to another piece of matter. Electricity can have a long-range force. Magnetism, if you feel two magnets that either pull each other towards each other or repel each other. And weight is a force that we're going to use. It is in reality gravity's pull on an object's mass, causing it to accelerate, but we're going to call it weight so we can more readily use it. The force of gravity on an object's mass is what weight is, how much gravity something's pulling on you with. Now, it has to do with the amount of mass that you have. Something that has more mass has more weight. But if you get up into space where there's no real gravitational pull, then objects have no weight, but they still have mass. Inertia is a value that we're going to use to describe objects in motion. Inertia is the resistance an object has to changing its state of motion. For instance, if this gentleman right here was driving along, and if he was to hit this stone wall or brick wall, and he was not buckled in, his mass would have a resistance to changing its state of motion, which means he would keep traveling forward even though the car stopped. This is why you slam into a steering wheel when you get into an accident, because your body keeps moving. And that's the purpose of a seatbelt, is to keep you held back as part of the car so that your inertia is counteracted. So inertia we're going to see a lot more later on. So a couple more ways to think of inertia. Inertia is the tendency for an object to resist changes in velocity. If you want to change your motion, you have to change your velocity, either your speed or your direction. So inertia is the tendency to resist velocity changes, which means if a change in velocity is an acceleration, then inertia is the tendency for an object to resist accelerations. This is why when you hit the gas at a stoplight, you feel like you're being pushed back into your seat. You're not really being pushed back, you're kind of staying still, and the car is coming up to meet your back and pulling you along with it. If you were to hit the brakes, you're not really being thrown forward. You're continuing the motion that you were already doing. Your car is slowing down, and you are going forward into your car. If you turn right, you feel like you're going left. You're not. You're actually going straight, and the car is turning into you. And vice versa. If you go left, you feel like you're going right, but in reality, you're going straight in the motion that you already had, and your car is coming to meet you. So you resist these accelerations of speed and direction changes, and that's what you're feeling is inertia. Inertia is related to an object's mass. The more matter an object has, then the more matter a force must act upon, more stuff to push or pull, which means more resistance. A Mack truck, for example, has a lot more matter to it than a Prius, and a Mack truck is a lot harder to move, either to push to speed up or to stop to slow down. A Prius doesn't have a lot of matter to it. You can push it by hand pretty easily. If it was going 1 mile an hour, you could get in front of it and stop it if it was in neutral pretty easily. So the amount of matter an object has is related to the amount of inertia or resistance it has. And even today, people are a little confused about that idea of inertia, resistance to changing motion. A lot of people think you need a force in order to keep something moving. You need to push something to keep it moving. That's because of one of the forces that we're going to deal with in this unit that people don't usually think about, the force of friction. Friction is that force that gives us that misconception that you always need to be pushing something in order to keep it moving. We'll get to that in a little while. Again, this idea of friction. Friction always acts against the motion of the object. So if I'm sliding something to the right, friction actually acts to the left. It always acts to stop an object from moving. It doesn't cause the motion, it stops the motion. So it's what's called a retarding force. It slows things down, stops things, turns things. It resists the motion of the object. So if this physics book on this table was sliding to the right, then friction is acting to the left to counteract that. So friction can also be thought of as a negative force. Let's identify some variables and some units for forces. 1 Newton is, newtons are the units for force. Obviously because Sir Isaac Newton was the one who identified the 3 laws of motion which deal with forces. So 1 Newton is equal to accelerating 1 kilogram of matter at a rate of 1 meter per second squared. So let's say I had a car that was 1 kilogram and I accelerated it at 1 meter per second squared. I would be applying a 1 Newton force on it. Now if you look at this physics book on the table on the left, the table is pushing upwards on the book, which is why the book's not falling to the floor. Let's say the table is pushing up with 20 newtons. If this book isn't moving, that means something has to balance it downward, maybe gravitational pull with a downward force of 20 newtons. On the right, if this book, same book resting on the table but being pushed, if it was suddenly released, it would slow down, it would come to a stop. That would mean there'd have to be a frictional force acting on it, maybe a 5 Newton frictional force. And we'll see how these forces come into play later on when we're talking about accelerations and balancing these. So Newton's first law said if an object is at rest or at constant velocity, it will stay that way unless acted upon by an outside force. Newton's second law says this is what happens when that outside force acts on it. The acceleration of an object produced by a net force is directly proportional to the magnitude and the direction of that force and inversely proportional to the object's mass. What this basically says is you push something, and if the forces aren't balanced, it's going to accelerate in the direction of the force. So if I want my car to get moving off the side of the road, if I push it, it's going to accelerate in the direction I'm pushing it. It also says that the acceleration rate is inversely proportional to the object's mass, which means the more mass there is, the less I can accelerate an object if I use the same amount of force. So if I use 10 newtons to push a small car, it'll accelerate. If I use 10 newtons to push a Mack truck, it'll accelerate, but not at the same rate as a small car. It'll be less of an acceleration rate because it has more of a mass. So Newton's second law says that not only do we have to look at the changing of the velocity, we also have to look at the mass of the object. This is what Newton's law looks like, Newton's second law looks like in a formula. Force equals mass times acceleration. The amount of force that you apply is equal to the amount of mass the object has and the acceleration rate in which you're accelerating it. And those are directly proportional to both are directly proportional to the force that's being applied. We're going to use this formula in a couple of different ways, changing variables to match certain situations. So keep it handy, make sure you write this one down. Okay, the same picture that we saw earlier. For Newton's first law, if your forces are balanced, that means there's no accelerations. An object at rest, an object in motion will stay at rest, will stay in motion. That's Newton's first law. Newton's second law says if the forces are unbalanced, then there will be an acceleration, and it will either be directly proportional to the net force or inversely proportional to the mass. I like to see it in this way, in this sort of map setup, because it kind of lets you see how both things, either staying at rest or in motion, or directly proportional to force and inversely to mass, you can see how they relate better. Let's see how we can change the force formula to match something a little more specific. The weight of an object is the force of gravity on an object's mass. We saw that earlier. Well, if force equals mass times acceleration, and that force is the weight force, which we'll use a W as a subscript, and the acceleration rate in which something's being accelerated by gravity is 9.8, which is little g, you can substitute that little g in for the acceleration, and you can use that W, the lowercase w, as kind of a new variable for force. We're going to call it weight. So weight equals mass times gravity, which is force, equals mass times acceleration. We're going to use this one specifically for weight, and in a lot of the examples you'll see me use W equals mg instead of F equals ma, and instead of other descriptors. I find it helps you separate from the multiple different ways in which we're going to use the force formula if they have very specific variables and setups for what you're trying to solve. So write this W equals mg down as another formula. Here's some more examples of how we're going to change these formulas. Your net force is what equals your mass times acceleration. In the end, once you add all forces together with vector addition, you'll end up with one resultant. That resultant is your net force. If you think about it like a paycheck, you have your gross pay and your net pay. Your gross pay is what you make in total. Your net pay is what you take home after you've added in all the or I should say subtracted all the taxes and health care and stuff like that. So your net is the resultant of all the other forces acting together. So your net force equals mass times acceleration. Your gravitational force, like we identified earlier, F equals ma, but if that F is weight and A is gravity, then you get W equals mg as another version of that formula. This one, the friction formula, doesn't follow that mass times acceleration. It follows a different formula, but it's that your friction force is equal to what's called your coefficient of friction times your normal force. We're going to get to these in a little bit as to what they are. Your coefficient of friction, that is the Greek letter mu, and your normal force is, normal in mathematics means perpendicular. So it's a force perpendicular to a surface. For example, if you're sitting in a chair right now, that normal force is perpendicular to the floor, and that's the force of the chair pushing back up on you. The normal force is a supporting force. If you rest something on a table, it's the support force from the table pushing back up on that object perpendicular to the table surface. If you incline that table, the normal force is now inclined. It stays perpendicular 90 degrees to the surface. So make sure you keep that one in mind. And we will write the friction force as a lowercase f and the normal force as a lowercase n. So we end up with this version of a force formula as well. This is just a small reminder of vector addition. You can look at it briefly. Remember, when you add vectors together, you have to maintain the directions, positive and negative. Usually positive is to the right, negative is to the left. The normal force, as I just described, is a force of an object that acts like a support force. For instance, the force of the floor on you causing you not to fall into the earth. Normal force is not like air resistance. That can be a supportive force, but that's not a normal force. Air resistance doesn't offer a solid support surface underneath you. So anything lying on the floor, anything sitting on your table, has a support underneath it from the floor and the table, and that's your normal force. And remember, it is always perpendicular to your surface. Here are some examples of some objects that are experiencing forces on them. This first one, if I look, I have F tension, that's a tension force from a rope or a chain, and I have F grav, which is the weight of the object. Now this object has a weight of 800 newtons, and there's a tension force of 1200 newtons acting up on it. If I add those together, 800 down, 1200 up, it's really a net force, write this in, a net force of 400 newtons up. That's my net force. And that I would use if I had the mass of the object to find the acceleration rate of this object upward. This one right here has an air resistance force of 600 newtons up and a weight of 800 newtons down, which means the net force on this is 200 newtons downward. This object is accelerating towards the ground and it's in free fall. This third one has a gravitational force or weight of 50 newtons, a normal force of 50 newtons, so I know this thing is sitting on something, and that normal force is perpendicular to the surface, and it's balancing out my weight. So this object's not going to be going up or down. It could be sliding along a table, it could be sitting at rest on a table, but if I look, there's 20 newtons of friction force to the left. Friction always acts against the motion of the object, which means this object is actually sliding to the right, but it's slowing down, because there's nothing acting to the right to balance friction. So you really have to get used to looking at the situations for these forces. So this object is sliding to the right, slowing down, and friction's acting on it, and it will until this object comes to a velocity of 0. Terminal velocity is the friction force from air as an object falls through it in free fall. So once the friction force from the air balances out with the weight of the object, then you'll stop accelerating, because if you remember from Newton's first law, if all forces are balanced, there's no acceleration. So if I have an object, like for instance, if I'm skydiving and I'm falling through the air and my weight is, let's say, 700 newtons, and I experience 700 newtons of air resistance, that means those two forces balance, which means no net force, no acceleration. I will have reached terminal velocity, or my final velocity for my object, which, if you remember, we had talked about for humans. If you're completely spread out belly flop style, you'll reach about 100, 130 miles an hour. If you're in a pencil dive, you'll reach about 200 miles an hour. And that it has to do with the amount of air resistance force that can hit your body because of the amount of surface area that you have. Here are some examples that we'll work through. If this large rock has a mass of 10 kilograms, its weight will be 100 newtons. A small rock with a mass of 1 kilogram will only have a weight of 10 newtons. They both accelerate at the same rate because their mass is proportional to the amount of weight that they have for each setup. It's a 1 to 10 ratio for either of these, so they accelerate at the same rate. And a person who has very light weight will have an earlier terminal velocity because their weight can be balanced out faster by air resistance. A person who's very heavy would have a lot more weight. It would take a lot more time for their air resistance to balance them out in order to reach terminal velocity. So we've seen these pictures drawn in the last couple of slides. Let's talk about what they actually are. It's a free body diagram. Free body meaning nothing connected to it. And we always draw a free body diagram as a box. If it's a person, it's a box. If it's a horse, it's a box. If it's a car, it's a box. The reason we do this is because a box has lines that are perpendicular to the x and y axes. So I can draw a perpendicular coming out, going horizontal and vertical out of a box easily. And we represent forces in vector form as arrows. And remember, you have to draw them proportional. You can't have a 10 Newton force the same length as a 100 Newton force. The magnitude of the arrow has to be proportional to the force, but you don't necessarily have to measure them out. They just have to look more or less. Here are some free body diagram examples. This first object has only weight acting on it, which means it's in free fall, but there's no air resistance. It's probably in a vacuum. This one has weight acting downward and normal force acting upwards, which means it has a support force. It's sitting on a table. This one has weight acting downwards and air resistance acting upwards. It's in free fall. This one has weight acting downwards and two tension forces acting upwards. This would be something like maybe a person hanging from the chin-up bar, and each one of these tension forces is the force in their arm, and the weight is their weight acting downwards. There's a lot of ways you can interpret these free body diagrams. So let's try this one out. What acceleration will result when 12 newtons of net force is applied to a 3 kilogram object? What about a 6 kilogram object? Well, let's list out our variables. We have a net force of 12 newtons. We have a mass of 3 kilograms. Let's say mass 1. We have mass 2 of 6 kilograms. My formula is F equals ma. So for the first one, 12 equals 3a. My acceleration rate will be 4 meters per second squared. My second one, same force, double the mass, 6a, which means my acceleration rate is 2 meters per second squared. Double the mass, half the acceleration. This is an illustration of Newton's second law, where more mass gets less acceleration for the same amount of force. Another way of looking at this same type of problem, a net force of 16 newtons causes a mass to accelerate at a rate of 5 meters per second squared. What's the object's mass? Let's write out our variables. Force, 16 newtons, acceleration rate, 5 meters per second squared. I want to know the mass. So F equals ma. So 16 equals 5m, which means my mass equals 16 divided by 5 is 3.3 kilograms. So it's a very straightforward, simple formula, but you'll see how we can use it to manipulate multiple different variables coming up. Okay, forces in 2 dimensions. This is where it starts to get a little more complicated, and this is the material that we'll really be focusing on during the meeting on Wednesday. You really want to get used to vector addition, taking a force or a vector that's at an angle and finding its components. It'll make it much easier if you can get everything into x and y components. So this object, for example, let's think about what's happening to this. I have weight of 100 newtons acting down. I have a friction force acting to the left, which means this object's moving to the right. I have an applied force of 80 newtons at 30 degrees. I have a normal force of 60 newtons. This object is being pulled on a surface by a rope. The rope has a force of 80 newtons at 30 degrees. It's like you're pulling someone who's on a sled and you're pulling them on a flat surface. I know which direction the person's traveling because it's the opposite direction of what friction's pointing. So this object is traveling in that direction. If I break that 80 Newton force up into its 2 components, if I was to break it up into like a triangle, where this is 80 newtons, and that is my x, and that's my y. Okay, if I broke it up into its components, I would have a y component of 40 newtons, an x component of 69.3 newtons, and then I can add these together. If you look, 40 newtons up from the rope and 60 newtons up from the ground is equal to 100 newtons of weight. It balances. This object is not going up or down because the up and down vertical forces balance each other. However, the 40 newtons of friction does not balance out the 69.3 newtons of x component, which means there's more X component from the rope than there is of friction, so this object is unbalanced. It's accelerating to the right by 29.3 newtons of force. This is the same example, but same idea. 200 newtons of weight, 150 newton applied force at 30 degrees, 125 newtons of normal force, and 60 newtons of friction. If you break that 150 newton applied force up into its components, using sine and cosine, just like the velocity components from Unit 2, you'll end up with 75 newtons of y component, just under 130 newtons of x component, and things will either balance or not. And if they don't balance, then you have an acceleration in a certain direction. Take a moment to pause the video and to look at situation B here and think of all of the things that are coming into play. Here's an example that does not have all of the information filled in for us. It looks overwhelming, but it's really more a matter of figuring out the puzzle, finding what variables you can calculate for first, and working your way around. If I look at this object, I have an applied force of 60 newtons acting at 30 degrees. I could break that up into components. X and Y components. Fy and Fx. I calculate these by doing Fy equals F sine theta. So my Fy equals 60 sine of 30. My Fy equals, that's a Y, equals 30 newtons up. My Fx is equal to F cosine theta. So Fx equals 60 cosine 30 degrees. So Fx equals 52 newtons. So I have components for these now. I've broken it up. I don't need to use that 60 newtons anymore. What are some other things that I can solve for? I have mass. I could find weight. So W equals mg. So my weight, which is this right here, equals my mass, 10 times 9.8, which means my weight equals 98 newtons. So I'll put that right here, 98 newtons. I also have my x component now, which this thing, friction is going to the left, so this object is sliding to the right, which means that my weight downward has to be balanced by both the normal force from the surface and the y component of the rope. If the y component of the rope is 30 newtons and my weight downward is 98, then all my table has to support with is 98 minus 30, which gives me 68 newtons. So I have my normal force now. 68 and 30 up balanced with 98 down. Now, I did give you the coefficient of friction, which we haven't gotten into yet. We'll talk more about this in the meeting on Wednesday. But just to show you how it's done, the coefficient of friction is the ratio between the friction force and the normal force. So it's really kind of the ratio between how much friction there is and how much these two objects are being compressed together. The harder you push two things together, the more friction there is. And the amount more is based on this ratio right here, this coefficient. So if I use my friction formula, friction equals coefficient times normal force, my friction equals 0.3 of my normal force, which is 68 newtons. So 68 times 0.3 gives me 20.4 newtons of friction. Now, I know that I have 20.4 friction backwards in 52 of x component. Okay, so there's 52 newtons x acting to the right and only 20.4 acting to the left. So I can find net force. My net force equals 52 minus 20.4. So my net force is 31.6 newtons. Now that I have my net force and my mass, I can do net force equals mass times acceleration. So 10 times 31.6, or I'm sorry, 10 and 31.6 is a net force. If I divide 31.6 by 10, I get 3.16 meters per second squared of acceleration. This may seem tricky and difficult and like a hard problem, but it's really just a matter of looking at what do I have to start with, what can I calculate now, and how does that relate to other things. It takes some time to get used to these. Forces in two dimensions are different inclined planes. Normal forces always act in a direction perpendicular to the surface. So this is what I was saying earlier. If my surface is flat, my normal force is at 90 degrees. If I'm on an incline, my normal force is still 90 degrees to that incline. So make sure you remember that, it's important. This is a force diagram of an object on an inclined plane. This would be the ground right here, and this is the incline, and it's made at this angle. And this is my weight, which always points downward, and my normal force, which is 90 degrees to the surface. Now that we have an inclined plane, we can't really use the x and y axis anymore because we're no longer on x and y terms. We are now going to use two different descriptions for kind of an x and y axis on an incline. We're going to use this idea of parallel to the surface and perpendicular to the surface. The parallel to the surface is going to be very similar to an x, and the perpendicular very similar to a y. If you turn your screen or tilt your head to the left a little to make the surface the x-axis, then you can see that parallel is x and perpendicular is y. Now any weight vector that you use, the angle of the ramp is going to be the same as this angle inside here. So if this first one, the angle is 30 degrees, so is this angle. And I'll show you that on Wednesday in class as to why that works. Now, when we do this, we create another triangle with the parallelogram rule, with this this parallel component. If you translate it down to the bottom of the triangle, you create a triangle with an angle. So to illustrate that, I will create this triangle right here with my perpendicular and parallel components, and here's the angle, which means my parallel component is equal to my weight, and it's opposite the angle, so it's sine theta. My perpendicular component is equal to the weight times cosine theta. And you'll see that as my incline increases, my parallel component down the ramp increases, my perpendicular component that holds the object on the ramp decreases. When we get to 90 degrees, that perpendicular component is gone, but so is the support from the surface. So you can see a relationship starting there between part of the weight and part of the support at 90 degrees. This is what I was talking about if you tilt your head. This is the original setup, an object on an incline with my parallel and perpendicular components. If you then tilt your head to the left, it looks like this now with an x and a y axis, but that's really the parallel and perpendicular axes. And you can see how that weight vector can be broken up into a kind of x and a kind of y component to balance out normal force and friction. Now we have something that looks very much so like the other problems we were just doing. Okay, Newton's first law says an object at rest or at constant velocity will stay that way unless a force acts upon it. Newton's second law says if a force acts upon it that's not balanced, it's going to accelerate, proportional to the force or inversely proportional to the mass. Newton's third law says that for every force that is applied to one object, an equal and opposite force must be applied back. So for instance, if I push on a wall, the wall will push back on me with an equal and opposite force. This is the interaction between two objects, and it's very tricky to understand in terms of accelerations, but think of it like if you were in terms of a frame of reference that's between two objects. Like if there was a baseball traveling towards a bat, if I could maintain a position in between the baseball and the bat as they move, I would obviously be moving, but as they move, if I could maintain a position directly between them, then it would look like they're both traveling at me at the same time. So it's very tricky to think of. Newton's third law really needs more demonstration on Wednesday for us. But if you think about it, you can break up forces into two different forces, action and reaction forces. So for instance, if I slam a door shut, when that door slams into the frame, the force of the door slamming into the frame is the action force. The force of the frame slamming back into the door to resist it is the reaction force. And that force has to be equal. You cannot push on something harder than it pushes back on you. So like I was just saying, forces always come in action-reaction pairs where one force is the action. This is typically the one that initiates the force, causes things to happen. And the reaction is the force that responds to it. I give the example in class, if you want to get out of trouble, let's say you were to smack somebody across the face, which you would never want to do because that's mean. But let's say you did. You could always assume the argument that according to Newton's third law of motion, your hand hit their face, but their face also hit your hand with an equal and opposite force back. So who's really at fault? It's kind of a tricky play on physics, but if you think about it, the hand is the one that initiated the motion. It is the action force. The face responded with the reaction force, so it makes it your fault. So you can argue it with physics, but you're not going to win. Another example, when a person pushes off a wall, the person's push is the action force, and the wall's push back on the person is the reaction force. So why does the person move and not the wall? Well, if you think about it, it's a combination. It's a chain effect. Person pushes on the wall pushes on the person. What does the wall push on backwards? It pushes on the ground, or the support surface that it's attached to. And then that support surface pushes back on the wall. And then the ground pushes on the earth, and the earth pushes on the ground. And what's the earth push on? Nothing. It's a ball in space. It will spin. You actually, when you push off of something, you cause the earth to spin. It's very hard to understand that your simple walking or your simple pushing off of things can cause a motion to the earth. That's because the earth is so big compared to us. But think about it, if you could shrink the earth down to the diameter of a log and you place it in the water where there's no real resistance force. If you're standing on that log and you start to walk forward, the log is going to spin backwards and you're not really going anywhere. So if you make that log a little bigger, it's going to be harder to move it. You'll need more force to move it. You'll get it moving a little bit, but you still cause it to move. Now make that log the size of the earth and you start pushing on it, as in walking. It's going to spin because there's nothing out in space that's acting to stop the earth. So it's really weird to think of that every time you walk or slam against a wall or slam a door or something, you cause a chain effect that goes directly into the earth. Here's a sprinter in some sprinting blocks. If the sprinter pushes off the blocks at the start of the race, what's the chain of action-reaction forces? Well, you have the sprinter pushes on the blocks push on the sprinter. That's one pair. The blocks push on the track push on the blocks. The track pushes on the ground pushes on the track. The ground pushes on nothing. There's nothing in space. If you think of the ground as being the earth, there's nothing on the other side. It's going to have to spin in order to counteract it. It's going to have to move. It's kind of like two ice skaters on the ice. If they push off from each other, they're going to go in opposite directions. So if you track that action-reaction chain back, when the sprinter pushes on the blocks back against the earth, the sprinter goes forward, the earth goes backwards, just at a very, very small amount. Because remember, acceleration is proportional to force and inversely proportional to the mass. So the earth doesn't have a lot of acceleration, whereas the person does, because the earth has a lot of mass and the person doesn't. Same example we just talked about, the baseball hitting the bat. The baseball is the action force, the bat's the reaction force because the bat had to react. The ball initiated the motion. But that force is equal and opposite between the two. The bat has more mass, so it will have less acceleration. The ball has less mass, so it will have more acceleration, which is why the ball goes flying off, hopefully in a home run, and the bat doesn't really recoil that much. So take a moment to write down the formulas that we found. I think we had 3 or 4 of them. And go through this slideshow. This is a very big unit. It has a lot of material to it. You want to spend a lot of time reviewing this. And on Wednesday, we will review net forces very briefly, and we'll get into 2-dimensional forces and forces on an inclined plane.